Hello, researchers. Welcome back. Today we are going to start talking about regression. And let me tell you, regression is the building block of all of our 21st century statistical techniques. I have done a number of different quantitative research projects, and every single one of them involved regression. Okay, so um, yeah, let's get started. You're going to be learning the most basic form of regression, ordinary least squares regression. But this is going to give you the foundation needed to understand research reports that use regression and also to do a little bit yourself. And it will provide a foundation, especially if you're planning on going on and getting your EDD, hopefully here at this university. All right. Okay. So regression. Regression to mediocrity. So Sir Francis Galton was measuring the heights of parents and their children, and he noticed that tall parents tend to produce offspring that are a little shorter than they are, and short parents tend to have children that are a little taller than they are. And he called this phenomena regression to mediocrity. Nowadays, we call this phenomena regression to the mean, with this idea that, most people are clustering around the center of a distribution, particularly when you're measuring something as simple as height, right? The basic idea to remember is that regression can be used to predict an outcome. Okay, this regression to the mean idea, meh. But the idea that regression can be used to predict. He was trying to predict how tall offspring would be given the heights of their parents. I don't know if he was right. I don't know what a modern calculator would tell you, but regression is used to predict. Now, Galton himself was the person who coined the term eugenics, and his work in the 1800s contributed to the forced sterilization of marginalized groups in the US in the 20th century. So, really took this idea of math and science and overlaid on it a lot of racist uh, ideas and tried to make this racism legitimate using math and science. So we don't like that part of Galton, but we're going to keep this idea about regression. Okay, so what can regression tell us? It can be used to describe the relationship between two or more variables, just like correlation can. Now, correlation quantifies the strength of the relationship, like how closely tied one variable is to the other. Regression quantifies the effect of one variable on another. So regression can be used to predict one score given other scores. So for example, if you know one thing has a medium effect, let's say that let's say that let's say here's one. Eating at Olive Garden, it may have an effect on someone's weight, let's say. Okay, and maybe there's a medium effect, right? So, depending on how many rich pasta meals you eat, that's going to have some effect on your weight. Now, let's say the only thing you eat at Olive Garden is their desserts. Okay, so not only you're going beyond just the pasta to these really rich cakes and other sweets, and that might have a large effect on your weight. So for each pasta meal you eat, it might have a medium effect on your weight, whereas for each time you eat dessert as dinner, that might have a larger effect. And then some things might have an extreme effect, but I can't even think of an analogy for that. That's what these graphs are illustrating there at the bottom. Slide 4, regression assumptions. These things need to be true about your data, or you shouldn't try to do a regression analysis with the data. First of all, it has to be continuous data. So interval or ratio variables. X can be dichotomous, but Y cannot. Okay. If the variables, and we're just going to be dealing with both variables being continuous in this class. If the variables are continuous, they are normally distributed. Okay. And in particular, the relationship between them should you'll see on the scatter plots. It's going to be similar to what we were talking about with correlation. Okay. There's a linear relationship between x and y, just like correlation. Regression doesn't understand curves. And there are a few others, but we don't have to worry about them for this class. A few other assumptions. Okay, so back to high school geometry, right? So I was taught that the formula for the equation of a line is y equals mx plus b, where x and y were the values for the x and y axis, respectively. And m was the slope of the line, and b was where the line met the y-axis. So that was the intercept. Okay. So reaching back into the mists of time. Yes, I went to high school in the 20th century. Okay. Many things have a linear relationship. That is, if we know one thing, we can calculate the other. We do this in our heads, or we let Google do it all the time. For example, if you wanted to convert from pounds to kilos, you would multiply in your head by 2.2, let's say. If you wanted to, kind of guess what shoe size you are, you've maybe your shoe size has changed recently. You might, measure your foot in inches, multiply it by 3, subtract 21, and that if you're a woman, that's your shoe size. If you're a man, you subtract 22, right? So we do these conversions, right? We hear a Celsius temperature, we basically multiply it by about 2 and add 32. And then we can convert it to Fahrenheit, right? We do these in our head because so many things have a linear relationship to one another. So let's look at a data example. Let's say we want to predict what a student's college GPA is going to be given their high school GPA. And let's say we have 10 students that we think are representative of the population of high school and college students, right? So we have these college students, we know their high school GPA, we're going to predict their college GPA. Okay, so first of all, I think I put this file in your, ooh, that's my mail, sorry. Wait, here we go. Yeah, I put it in your, yeah, here we go. GPA prediction data file. All right, there we go. And then I'm going to slide down and hit download. And here, let me minimize this so you can see. Okay, this is an Excel file. All right. And so let me save this on my desktop. Save as, where's my desktop? Wait, lost the folder. Ah! Sorry. Okay. Save as. And I like to go through this even though it can be a little awkward at times. Okay. So that just so you see. Okay, wait, no. Get me out of there. Just in case something you see that I do, is helpful to you at some point. Save as, yeah, that's my desktop. Okay. And save. Okay, so now I'm going to close Excel. And where is SPSS? I'm going to open up my SPSS. And there we go. There's a splash screen. Okay, it's asking me if I want to open a previous data set. I don't, so I'm going to X out of there. I'm going to go to File, Import Data, Excel, and I put it on the desktop. Desktop. Okay. GPA prediction data file open. Okay, now it reads the file. I told it to read, and I tell it to read the variable names in the first row, and it looks like it got student. The students had a number. They had a high school GPA. Why is this 2.99999? And they have a college GPA. That's so weird. Okay. Um, and that looks right in their little, this is the guess, the preview is what SPSS guesses the data should look like, and that looks about right. I'm going to hit OK. And then here is our data editor, right? And it's called Untitled 2 with a star. That always makes me nervous. I'm going to save it, save as, and it's on the desktop. This is GPA prediction, and it'll save it as a dot save, which is what the SPSS files. Okay, so we have this. I put something at the bottom as a reminder for everyone. Okay, I put in the Excel file, always check the file. Okay, this is not right. This is not a person. Okay, it should be every student had a number. They had a high school GPA, they had a college GPA. If I don't clean this up, okay, if I don't clean this up, then this is going to mess up my calculations. All right, so always look through and check your file. I'm going to highlight. Now, can I get rid of the student, this fake student at the bottom? Data, is it a data? Edit. How do I delete a case? Can I just hit cut? Oh, yep. I hit edit cut and it deleted that case. It deleted that line of data. Okay. And so now this is my data editor, right? Let's look at the variable view. Oops. Sorry, let me make sure this is so you all can see. I'm going to switch to window syntax. No, I want the variable view. Oh, there's a tab on the bottom, which I can't get y'all to see, but here we go. I click the tab on the bottom. Okay, so now here's our variable. Okay. Says student string width of 6, and it's a nominal. But in actuality, the student was supposed to be a number, but it had that always check the file at the bottom, which told SPSS it was a string. It's supposed to be numeric. So I'm going to change that variable type to numeric. I clicked on it. Okay. Okay, then was high school GPA, and it took out the spaces that were in my Excel column heading, which is exactly what it should do because variable names should not have spaces. High school GPA should be numeric. If it's not the right type, data SPSS won't be able to do calculations on it. And college GPA should also be numeric. Okay. This was, I like to name, you remember how I like to make it clear when something is an ID. Ooh, it's saying, saying your name contains an illegal character. Did anybody see what I did as a mistake? Yep, I put in a space and I wasn't supposed to. Okay, there we go. Student ID. Okay, now GPA, is that categorical or continuous? GPA. If you said continuous, you are right. So I need to change these to scale. They're not nominal. If it's not the right type, then because regression can only be used with scale data, if it's not the right type, either SPSS won't let you do the calculations you want to do, or it will do them making assumptions that are not true for your data. If your data is identified in terms of the measurement type, okay? And you'll get results that you don't expect and you don't want. Okay, can you tell I've made a lot of mistakes? I have made a lot of mistakes while doing data analysis. So I'm pretty familiar with a lot of the errors you can get. Okay, so first thing we always are going to do is we're going to get some descriptive statistics on our data. So analyze, I can go to descriptive statistics. Let's do frequencies again. And student ID, we don't need, that's just to identify the students. But for high school GPA and college GPA, we definitely want some descriptive statistics. I would like the mean, please, and the standard deviation. That's all I need for this. Continue. I don't need the frequency table, but I do need a histogram. Okay, because remember we're looking for normal distributions of both of our variables, our independent and our dependent variable, our predictor and our outcome, or mostly normal. Okay, let's look at what we get, what output we get. Okay, so over here, I see that we have 10 valid high school GPAs and 10 valid college GPAs. Good. And that's because we deleted that really, that line that was just a reminder to look at your data. The average high school GPA was 2.81, or mean high school GPA was 2.81, with a standard deviation of 0.559 points. The mean college GPA was 2.64 with a standard deviation of 0.582 points. So high school GPA was higher than college GPA on average. And let's look at this distribution. Okay, looks like we have, that doesn't look normal. It looks a little bit skewed, but it's basically mound shaped. I'm not too worried about that. I think we can go ahead and do regression with that. Oh, college GPA really does look normal, and it's, see how it's symmetric? Symmetric, it's not skewed. Okay, so now let's go back to our slides. Oh, scatter plot, yes, of course. So just like with correlation, with regression, we want to do a scatter plot. So I'm going to go to graphs. I like these legacy dialogues because it makes it easy. I'm going to slide all the way down to scatter dot and choose simple scatter. And then now I need to define. Okay, what predicts what? On the x-axis, we're always going to put our predictor. On the y-axis, we'll put our outcome. On the x-axis, our independent variable. On the y-axis, our dependent variable. Okay, so we're going to go from predictor to outcome. So what comes first is high school, right? So we'll put high school on the x-axis. We're using the high school GPA to predict the college GPA. So college GPA goes on the y-axis. And I'm going to hit OK. And now here's what SPSS gave me. Okay, see? Look at that. Looks pretty linear, doesn't it? Nice line. Pretty well lined up there. Okay, so this graph, I copied and pasted it or something similar into your slides here. And so there we go. That's the scatter plot. We always want to look at it. We want to make sure that it looks linear. And it does. All right, next slide. Oh, okay. Does it look like there's a strong correlation? Yes. The you could really see the dots kind of lining up pretty close. If you were to calculate it, you could calculate the correlation. You would find that it came to 0.91. So a high school GPS is strongly related to having a high college GPS. But how much? If you know the high school GPA is 2.0, what would you expect the college GPA to be? If we know the equation of the line, we could plug in the value for high school GPA and predict a value for college GPA. Okay, so predicted scores would go on the line. The data that are the dots. Okay, that's what we observe of our sample of 10 hopefully representative students, right? So we have but we're going to predict like this line represents the average. Okay, along each high school GPA, the line is plotted what we think the typical college GPA would be. Okay, so the method we are learning is also called linear regression because we're predicting it and we're assuming that there's a linear relationship. Okay, we can use the formula y equals, and I just, sorry about all these bells going off. We can use the formula for a line that is very similar to y equals mx plus b. Let's say y equals bx plus a. All right. And there are other ways to write a regression formula, but let's use that one. You could write it y equals a plus bx. Okay. The main thing is that you have this constant or this number that's standing alone, and then you have a number that is next to a variable. Okay. And when we're doing a regression analysis, that the number that's next to a variable is what we're predicting is going to be the slope of the line, right? And that's basically what we're trying to find out using our SPSS app. Okay, so when we're doing regression analysis, we use y hat to indicate that y is predicted. It's theoretical. It's a theoretical value, not the one that we actually measured, not the one we actually observed, but what we're predicting. So we put the little hat. Where's that on the keyboard? Oh yeah, above the six. Above the six. So there's a way to do it, and there's also a way you can use a formula editor. I don't know, how did I do this? I don't know how I did that. Or you can always copy and paste from a slide. Yes. Okay. B, the slope, is the amount of difference in y that we predict will happen if there is a 1 unit difference in x. Okay? In other words, it is the size of the effect that x has on y when x is higher by 1 unit. A is at the point where where the line crosses that y-axis, the intercept. It's still the intercept. It's what we predict y will be when x is 0. So if high school GPA goes from 0 to 1, we expect y hat college GPA will go up from minus zero point zero 0.02 to 0.93. And the way I know this is, how do I know this? Where does it say? It doesn't, I didn't show you how I got that calculation, but let me show you now. Okay, so this is the formula. Okay, predicted college GPA, the last line. Predicted college GPA equals 0.95 times the whatever the x is, the high school GPA minus 0.02. Okay, all right. So all right. So let me show you how you get that in SPSS. So there was my graph, my scatter plot. And I'm going to go analyze and slide down to regression, linear. My independent variable is high school. My dependent variable is college. Let me see what's under statistics. I need my estimates. Model fit is good. We're going to be talking about that later. That's good. Where's options? I will always want to exclude cases list-wide, and I want to include the constant in the equation. Continue. Okay. We don't have to worry about anything else. And hit OK. All right. So it says that we entered high school GPA as our predictor variable, and our dependent variable, our outcome, is college GPA. We're going to talk about what this means soon. It gives this is about your equation overall, but what we want are the coefficients. Sorry, trying to slide this up. Yes, down here at the bottom. We see our constant is minus 0.027. That is our intercept, okay? We see our high school GPA, the parameter associated with our high school GPA. The slope of the line is 0.949, okay? And we see that's statistically significant. Okay, but let's go back to our slides and I'll explain this a little bit more. So 0.949 is close to 0.95. And minus 0.027, that should be this should be 0.03. Yeah, because you round up. 0.03, 0.92. Okay. Yep, we want to be precise. Okay, so how do we determine if this line is the best one? Actually, you don't have to determine it yourself. This is part of what regression does. It's minimizing the distance that the data points are from the line. It's kind of like variance. Instead of deviation from the mean, we're concerned about deviation from this line, okay? And it's minimizing the difference. And if so we can we can we can, but we don't want to. This line of best fit is what SPS is figuring out. Okay, minimizing the distances, and you can imagine that calculus is involved, right? Because then you're minimizing the sum of the squares. All right, which yeah, some of us did years and years ago. Some of us didn't. That's okay because we've got SPSS. All right, and so that's basically the logic of how this is working. Okay. There's the formulas. GPA prediction. Okay. So we get this in this, yeah, formulas. Um, um, we get, you could solve it with, yeah, using formulas, but we won't. We get this formula, and this should be minus 0.03. That's in the purple box. See that? So y hat equals bx plus a. Our predicted GPA, and let me write this in English. Predicted college GPA predicted college GPA. Can y'all see that? Equals, let me start a new line, 0.95 times the high school GPA minus 0.03. See that? So now all we would have to do, let's say 2.0, is plug in 2.0 as a high school GPA, and we could figure out what the predicted college GPA was going to be. Just in case you have a high schooler at home and you want to see how they're going to do in college. Of course, there's a lot of individual variability, right? So this is just our best guess based on made up data, actually. All right. And so what we would do is we would show in our report, we would have our scatter plot and a line. You don't want the line to go beyond your data because we really don't have no idea what happens between a 0 and a 2 of a high school GPA. So you don't want the line to go beyond the data. Why does this line go beyond the data? Okay, you don't want that. Delete. Okay. Only make predictions within the bounds of your data. So from your minimum high school GPA to your maximum high school GPA is the only these are the only places you can make predictions. We can now use our our formula, and again that was minus 0.027, which rounds to 0.03. So this should be 0.03. If my cousin's high school GPA is 3.7, what do we expect his college GPA to be? And we would plug in 3.7 into our formula. So y hat equals 0.95 times 3.7 minus 0.03. So this would be 4.8, which is still about 3.5. Okay? So we expect him not to do quite as well in college. College is a little bit harder than high school. All right. And that's basically how you can use regression to predict. So hypothesis testing. Okay? Let's talk about that for a minute. We know how to create our line and measure how well it fits. Now, how do we use it to test a hypothesis? The null hypothesis is that there's no relationship, right? It should be underscore subscript. Okay. So I know that there's no relationship between the predictor and the outcome. So the slope would be 0 if there was no relationship. What you'll see in your SPSS printout and also in papers is actually a t-value because the t-distribution is what is used to predict this. But it's not actually, we're not actually doing a t-test, we're doing regression. But what you'll see is a t-value. And you would look it up on the table and reject the null if t is more extreme than the critical value on a table. But SPSS will give you the p-value, so you don't have to look it up. It's doing the looking up for you, and p should always be italicized because it is a statistic, just like t. Okay. So I circled it here on the output, okay? First of all, making sure that it has the right predictor, in this case, high school GPA. And you want it to make sure it has the right dependent variable. And what you're looking for is the coefficients, okay? And you see I circled for the constant and for the high school GPA. Those are your coefficients. And then the second to last column is your t-values. You don't have to, first of all, for the row that's constant, you don't have to worry about the t-value. See that minus 0.062 and the p-value of 0.952? Don't have to worry about the t-value for the constant. You do want to look at the t-value for the for your slope and on the high school GPA line. And that T is 6.2777. I would probably round it to 6.28, sorry. And P is 0.000, which we're going to write as P is less than 0.01. Okay, it tells us the likelihood that the slope of X. The relationship between X and Y is 0 in the population. As usual, if our p-value is below 0.05, we reject our null hypothesis and say that there is a relationship between X and Y, that is not 0. Okay? If it's above 0.05, we fail to reject our null hypothesis. In this case, we reject our null hypothesis that there is no relationship between high school GPA and college GPA. Okay, then there's some on the slides about standardized coefficients. Um, Basically, bottom line is if you standardize the coefficient, you actually get R, the correlation. But that only works if you only have one variable, one predictor in your model. Okay, and I just wanted to show you that you can calculate the correlation, and that's the same as your standardized coefficient. But we're not really worried about that because we're using unstandardized coefficients. But that's what this is in this second, this one, two, three, fourth column. See, I circled it in purple there. All right, so I just wanted just a little, side thing to show you. All right, that's the end of part 1. Okay, see you next time. Bye-bye.